Well, actually, first I would like to thank the organizers for this wonderful meeting. And well, as the title says, I'm going to talk about some challenges that the concept of a cosmic self-acceleration from modified gravity faces, in particular when confronted with the combination of gravitational wave and large-scale structure observations. And then when I say here modified gravity, what I really mean, I will restrict to Horndeski theories. And because it's late, people are probably waiting for the coffee break, I'll give you the conclusions first. And well, the idea here is that in Horndeski theories, there's two ways you can produce a self-acceleration. Either it's coming here on the y-axis from some change in the effective gravitational coupling, or some modification that also yields a deviation in the gravitational wave speed. Or really a combination of both, and that's this blue dark shaded region here. And then we can use large-scale structure to constrain either this running coupling or this modification that also gives deviation in the speed of gravitational waves individually. But then there is a region in parameter space where these two effects conspire to reproduce the same large-scale structure as lambda ZM. And this dark degeneracy really extends all the way into this self-accelerated regime, where you have a parameter space where you can produce the same large-scale structure as lambda ZM, the same expansion history, yet you produce cosmic acceleration really from something different than a cosmological constant, really a modification of gravity. But as you can see from this plot, this degeneracy is broken by measuring the speed of gravitational waves, for instance. And further in the future, we can also use gravitational wave distance that are inferred from the decay of the gravitational wave amplitude with 1/4 distance. If you can measure the redshift with some electromagnetic counterpart, you get a luminosity distance redshift relation, and you can compare that to what we get, for instance, from supernova, and then constrain this effect in the gravitational coupling. And yes, as I said, conclusions first here. The first conclusion we'll get to is, well, it is just mentioned that large-scale structure without gravitational waves cannot fully discriminate self-accelerate modified gravity from a cosmological constant. But if you have gravitational wave observations, you break this degeneracy. Then the second conclusion that I'll try to get to here is that we will see that Horndeski gravity will no longer be a candidate for explaining cosmic acceleration, maybe as soon as already October. And connected to that is a third conclusion, that covariant Galilean theories are no longer going to be a viable model for gravity. All right, so first of all,
So I have a question about the GR plus lambda is a class of Horndeski gravity. So what do you mean?
well, okay, fine. Without any contribution of dark energy. I'll actually get to this right in this slide here. So essentially, the question here is, can this action produce cosmic acceleration, a self-acceleration that really comes from modified gravity? And I do not mean anything that you plug into G2, because that's just dark energy. But really something from the other functions. And you can see there's really lots of freedom. We have 4 functions, both of the scale field phi and the square of the derivative. So you'd naturally expect that this thing should be able to explain cosmic acceleration really as an alternative to some dark energy part here. And first, of course, what we need to I don't want to define here what I mean here by self-acceleration. And I will restrict to so-called genuine self-accelerated effect from modified gravity. And that's different from what you could call kinetic self-acceleration. Maybe I'll have time to mention something about that at the end. And the idea is here so that if you make a transformation, if you write down your Einstein equations, the modified Einstein equation in Jordan frame, you have some complicated geometric part on the left-hand side, and you just have your minimally coupled energy momentum tensor on the right-hand side. And in this situation, actually, we observe cosmic acceleration. But now if you do a transformation into Einstein frame, this really only needs to apply to the background. That's why I call it here a Einstein-Friedmann frame. You don't want to see this acceleration, because in this situation you just have the normal Einstein equations with your Einstein tensor, and on the right hand some exotic matter or dark energy contributions. And if you see then cosmic acceleration, this can really be attributed to some exotic stuff you added here instead of really a modification of gravity. So what we want is basically, well, we observe that the scale factor in Jordan frame is accelerated at late time, somewhere below redshifts of 1. But it is never accelerated in, or at late times in this Einstein frame. And you can make the transformation between these accelerations with a conformal factor omega here. And you can see this thing is positive at late times, this thing is positive, so that means, of course, to bring something positive to something which is...
The technical assumption is the physical assumption. So you are asking...
I'll give you one more thing, how to an alternative view how you could see this, yeah. So I'm just saying, so if you want to bring this from positive to negative or smaller than equals 0, the conformal factor needs to evolve at order unity. I guess that, two positive things, this thing should not be positive. Okay, so another way you could see it, maybe more physics, more fundamental here, is that you want the thing that is driving cosmic acceleration to be something that comes from modified gravity, should be the thing that defines here the modification of gravity. And you could say, well, what's really underlying this is a breaking of the strong equivalence principle. And that thing, at least for the cosmological background, that thing should be really what drives cosmic acceleration. You could even say, well, maybe there's just a dark sector interaction. You would well say, well, then it's the weak equivalence principle that should be broken in order to achieve cosmic acceleration. And the two descriptions are equivalent. Okay, so instead of working with the full Horndeski theory, what I'll do, I will adopt this EFT formalism that we've already heard a lot about, so I don't need to say anything about this. Basically, it's just for the background, we have the Hubble parameter, or you could use just a scale factor as a free function. Then we have 4 free functions that describe the linear cosmological perturbations. This is the kineticity, evolution in new gravitational coupling, or the Planck mass, a braiding term, and also modification that yields deviation, the speed of gravitational waves. Okay, if you go then back to this inequality that we had before, oh God. Yeah, it's Cortana. All right, so so basically what you can see, we can relate this to this evolution in the conformal factor to these EFT functions, that what we find is that this cosmic acceleration, self-acceleration effect should really be coming from an evolution in the gravitational coupling, or something that also deviates, introduces deviation to the speed of gravitational waves from speed of light, or really a combination of two. And they really have to add up to an order unity effect. Let me skip this. So, okay, so what will we test then with large-scale structure? Basically, we write down again this modified Einstein equation with complicated left-hand side and geometric part. And what you can now do is you just move everything that's on the left-hand side that is not GR, not the Einstein tensor, to the right-hand side. And you just declare this as some effective dark fluid. But then, since we had, we're in Jordan frame with a minimal couplet energy momentum tensor, and we have the Bianchi identities, that means we also have conservation of this effective dark fluid. And that means we can apply the usual cosmological perturbation theory. So we have here 4 scalar metric perturbations, 4 matter perturbations. Then we have the Einstein conservation equations that fix 4 of those. And 2 can be fixed by adopting a particular gauge. And so we really just need 2 closure relations to close the system of differential equations. And those are typically what our gravity theory feeds us. I mean, if you take GR or modified gravity theories. And typically, I'm sure everyone is familiar with this here. We can go into a Newtonian gauge, and you would then parameterize this, for instance, with a deviation in the Poisson equation or a gravitational slip. And in GR, we just have, mu gamma equals to 1. But in Horndeski theories, this is a bit more complicated. And now you could say, okay, I'm just measuring with observations mu gamma at the background, so I have 3 constraints. In principle, you could maybe make use of the scale dependence. You get 5 constraints, you constrain all the 5 functions in Horndeski theory. You can rule it in or rule it out. Unfortunately, it's not as easy, as simple, as we'll just show in the next slide. So let's just do this more systematically here. You can go to the small scale limit in mu and gamma, and you get 2 constraints. So for 5 functions, it reduces to 3 free functions in this EFT formalism for Horndeski theory. One actually only acts really beyond it's only going to be important beyond the sound horizon, or beyond the quasi-static limit. But it's like, okay, maybe I can use the scale dependence. So you include that as well, and you say, let's see what happens if mu and gamma is equal to 1, like in lambda CDM. And then you don't get 2 extra constraints, but only 1. That's the particular way the perturbations work out. So you can always pick here a a Horndeski theory that has mu gamma equals to 1. On top of that, an expansion history that looks like lambda CDM, and you can even choose it to self-accelerate. So that's a problem for large-scale structure. And just to show that you can really construct these models, so we can do this here. We pick here, the 5 EFT functions for our model. The first thing, of course, is expansion history of lambda CDM. Then we want a second function. And here I want to have a model that is truly self-accelerated. So I go back to this definition between the difference between Einstein and Jordan frame. These are the accelerations of the scale factor. So just multiply by -1. So you can see here we have a positive acceleration in Jordan frame at late times. But in Einstein frame, it's never turning positive. And here, basically, the modification, this conformal factor I'm introducing here is just deviation around unity, like GR, with some amplitude and a power law that increases the modification faster than the matter decays. Okay, so I'm reducing now this amplitude, and you can see how this thing comes down. And at some point, I hit the threshold. If I reduce the amplitude further than that, then I'll get to a model where I really have added dark energy in order to achieve cosmic acceleration. So I'll just pick here the threshold of omega plus of -0.1, and that defines my second EFT function. Now I don't want this thing to cause any modifications in the large-scale structure. So I introduce here these linear shielding conditions are basically what produces this dark degeneracy. That gives me two constraint equations that fix the other two EFT functions, third and fourth, and so basically I'm left with the fifth. And here I can just pick the sound speed to be the speed of light, and then have fully defined my Horndeski theory. And now you could even go on and say, well, this is still an EFT, and I want to see a covariant theory for that. And that's something that you heard Joe's talk yesterday, that you actually can do this. You can now go and construct a covariant theory that gives you this. But yeah, then maybe it convinces you this is really a modified gravity theory. You can see on the left-hand side these alphas. They are clearly not GR, not lambda CDM. They're going up to over 10% effects at late times. And then you say, okay, let's compute these perturbations now. And these are the full perturbations with time derivatives. And what you can see here is these solid color curves. Those are the perturbations you get in lambda CDM. Of course, you don't have a scalar perturbation. And the dotted curves below that are the perturbations you get from this modified Horndeski theory that gives you cosmic self-acceleration. But you can see it produces exactly the same perturbations. And this is evaluated at the Hubble scale. So if you would expect any deviations to appear somewhere than at the Hubble scale, but you can't see anything. So yeah, that's a problem. You cannot discriminate that from lambda CDM with large-scale structure. And maybe you say, well, model may not be healthy, but you can go and check this, and it all seems fine. But of course, from the first slide, you know you can break this degeneracy by considering gravitational waves. And there's two effects that you can see here in the propagation of the wave. And one is an extra friction term that you get on top of the Hubble friction that changes the damping, so the way the amplitude of the gravitational wave decays with distance. And the other thing is, as I mentioned before, a change in the speed of the gravitational wave. You can test the speed by comparing arrival times. For instance, if you have a gravitational wave observation and some electromagnetic counterpart, you just compare the two signals, you get actually very, very strong constraints. And the second thing, yeah, the damping of the gravitational wave, of course, that can be tested with standard sirens, as I mentioned before, further in the future. And, well, okay, so let's go back to these two constraint equations that we need to produce the same, to essentially produce mu and gamma equal to 1, like in GR. And one constraint is a complicated nonlinear differential equation between alpha m and alpha b. But for our purpose, the other one is more interesting. You can see it's just relating alpha t, the deviation speed of gravitational wave, to alpha m, which is the evolution in your gravitational coupling. And then, if you remember, the self-acceleration condition that we had here, this evolution in this conformal factor, requires some deviation in the same terms at order unity. So that means now, of course, that if we measure alpha t to be 0, there's two things. First of all, that means that the self-acceleration effect has to really come purely from an evolution in this in the coupling, the gravitational coupling, the Planck mass. And the second thing you see is, well, this thing should be order unity, so this thing should be order unity, but this thing is 0. So you've broken the dark degeneracy. And well, that also means that, of course, because this needs to be order unity, the self-acceleration effect shows up at order unity in your large-scale structure. Now, this is exactly what the plot I showed in the beginning. So we can have self-acceleration either from this in alpha m or in alpha t, or a combination of the two. It should be somewhere around order unity. So with large-scale structure, we can put good constraints on either alpha m or alpha t, but then there is this region in the parameter space where we get this dark degeneracy, and we can get self-acceleration from a modified Lansky theory that you cannot distinguish from Lambda CM. But then, yeah, you break this degeneracy with measuring the arrival times, and you could also break it actually with standard science, but that is further in the future. Now, these are constraints forecasts from Euclid. And what I want to show you next is that actually, well, basically what we have is if we measure this arrival times, then basically it means that a self-accelerated solution should occupy this upper left corner. And what I want to show you next is that we already have large-scale structure data that push below this bound. All right, okay. All right, so for that, I will set alpha t to 0. And, well, I think there are already good motivations without having the direct measurement from just what Anne mentioned before, for instance, from cosmic rays that do not, well, the pure fact that we actually observed them, that they haven't decayed due to Cherenkov radiation, gravitational Cherenkov radiation. Or the binary pulsars that can put percent level or sub% level constraints on alpha t. But of course, a direct measurement, like a counterpart measurement to a gravitational wave, could be much more interesting. And I'll just mention a bit more about this just in the next slide. Now, as I mentioned before, cosmic self-acceleration must now appear from a running of the gravitational coupling at order unity. And now if we go back to this condition of producing self-acceleration, this inequality, you can see that this is actually just a relation, well, a differential equation for alpha m. And we can integrate that, and then we get the minimal evolution in the Planck mass that is needed to produce a pure self-acceleration. And this is actually fully defined by the expansion history, which I chose here to be lambda m, because I'm interested in the minimal deviation around lambda m. But the modification is not yet fully defined. We don't know yet what alpha b is, the braiding term. And for that, you can go and look at the small scale limit of the modification in the Poisson equation, and you realize that the only way you can minimize this effect away from lambda CDM is by setting alpha b to alpha m. And that fixes your model. So that's the minimal modification, self-accelerated modified or Lansky modification of gravity that that you can consider here. And it is really small. I mean, you can see here what we modify is essentially the small modification of Poisson equation. It has to be an enhancement of gravity because, or of clustering of the Poisson equation, because of, that's directly coupled to the self-acceleration that we need. Gamma is 1, like in GR. And what we then have, of course, is very small modification. So mu is 1 all the way down to redshift of 1. Of course, we don't need a modification before that, because then that's where cosmic acceleration kicks in. And then it goes up to only 4% effect today. So it's very small modification. Yet, as we'll show next, that's something that we already can say about this with current data. Now, the first thing I'll do, we'll just do a comparison with cosmological data and pick some background data just to constrain the cosmological parameters. But then also look at perturbations, so temperature, polarization, lensing, cross correlations. Then we also have here this EG quantity, which tests the combination of galaxy clustering, lensing, and growth data. But particularly important for this exercise here is the galaxy ISW cross correlation. And you can see that here on the left-hand side is just one of the 9 samples we've used. The blue curve shows the prediction for lambda ZDM. And the red, or the best fit, red dashed curve is the prediction from this minimal modification that you can do to get self-acceleration. And you can say they do well, they do predict a different signal here. And you can even see, particularly here on the high multiple end, we get even anti-correlation, which we clearly don't have in the data. Now, why is the ISW so interesting to test cosmic acceleration? Here you can see this directly. Basically, what we're testing is an evolving lensing potential. And that's this sigma prime here, and that's directly proportional to alpha m, the running of the gravitational coupling. And that is exactly the thing that is supposed here to cause cosmic acceleration. So it's very sensitive to this effect. Now, we do then an overall fit to this data, and what we find is that lambda ZM fits, well, actually this minimal modification you can do fits 3 sigma worse than lambda ZM. So we get strong evidence here for a cosmological constant over a modification of gravity. Yeah, it's mostly from the ISW. Mostly. But it's really...
Is that, so you said you have 9 such...
Yeah, this is data by Shirley, who... Actually, it's funny, it's from 2008, so it's not new data.
And the difference between those 2 curves? Is
Well, it's one of 9 samples.
So it's pretty similar once you take into account all of that?
Yeah. And I think one shouldn't be too surprised about this, because we have seen this over and over again in subspaces of Lansky theory. In FFR gravity, in DGP, in Galilean gravity, and I think actually Alex is going to talk more about this on Thursday. And actually, yeah, they have here, for instance, you find the cubic Galilean to be, Miguel as well, the cubic Galilean, something like 7, 8 sigma standard deviations away from the data. All right, so, well, then let's talk a bit about NGC 4993. So what's that? That's an elliptic galaxy in the Hydra constellation. It's about 40 megaparsec away from us. And on the 17th of August, it's been rumored that they've detected here a gravitational wave emitted from a neutron star merger, which also sent out some trigger to electromagnetic, well, to other telescopes that should look for electromagnetic counterparts. And I think they did observe a short gamma ray burst from the same system. They did detect this object also in X-ray and UV from the afterglow that you can look for after a short gamma ray burst. And these observations are immediately made public, so when we know that there's something going on, something happened in this system. And now what would be the implications now if we detected indeed a gravitational wave with an electromagnetic counterpart? You can imagine this system, the light has been traveling for 120 million years. And that means if the gravitational wave and the light arrive here at the same time, that's constrained on the speed of gravitational waves away from the speed of light at the order 10 to the minus 15. And you could turn this around and say, well, okay, for something to be cosmologically interesting, it should at least be a % level modification. And that would imply that one of the signals should actually lag 1 million years behind the other. So once this is measured, alpha t for all practical purposes in cosmology is 0. Okay. Well, then brings me back to the conclusion. So we had, well, I showed you first that large-scale structure alone, without gravitational waves, cannot fully discriminate between self-accelerated modified gravity in Lansky theory from a cosmological constant. And I think that's something to keep in mind when doing parametrized tests. If you really use all the 5 free functions in Lansky theory, and in principle, you should recover this degeneracy. And if you don't, you've basically just constrained your choice of time parameterization you plugged in. But luckily, well, we may soon get rid of that problem if we have a counterpart measurement. And in that case, I hope it could convince you, Lansky theory will have a problem in explaining cosmic acceleration. And this could be happening as soon as October, because actually as far as I'm aware of, LIGO has scheduled a symposium for mid-October where they're going to talk exactly about the counterpart measurements to gravitational waves. They may even have a press conference, which, okay, I'm not in LIGO, so I don't know these things. So. But on the other hand, you could say, well, in the past I've used a bit more time to analyze the gravitational wave signals, so maybe we'll take a couple of months more until we really know what happened. And, well, that brings me also to the Galilean theory. You know, the cubic Galilean, as I just mentioned, is producing also an anti-galaxy ISW cross-correlation that can be ruled out. But the quartic and quintic models, they change the speed of gravitational waves. And so if alpha t 0, that will be gone too. Okay, and that's pretty much all I wanted to talk about, so thank you.
Well, first of all, there is a comment that only quartic and quintic Largescale terms, they change the speed of propagation for gravitational waves. And there was a recent paper by Harvey and Real, sorry, it's one person, Harvey Real, who actually, it's like Karl Marx and Engels, but who actually showed that these terms, they don't obey strong hyperbolicity condition. So from the point of view of a normal Cauchy problem, anyway, these high-order Largescale terms are not very welcoming. On the other hand, of course, one may try to exclude the cubic Galilean term, which actually just is x plus x multiplied with box phi, so kinetic term multiplied with box phi. But from the point of view of kind of effective fluid description, it's not necessarily x. It can be a very actually complicated function of x in front of box phi. I don't think integrated Sachs-Wolf effect will actually anyhow cure that, or anyhow constrain that, right? So it's as good actually as quintessence or quiescence in that sense.
Right. So the x box phi is giving you this 7, 8 sigma, but you could consider other powers of x.
Of
sure.
course.
Yeah, but I think so.
And let me just say is that actually there is no real reason from the point of view of hydrodynamics to have x box phi, because this function in front of box phi encodes kind of your diffusivity or whatever, and it can be, and it's most probably, if it is at all there, it's a very complicated expression in x. It's never linear in
so
x.
this is what I called in the beginning is kinetic self-acceleration, not the type, not the genuine type. And we are currently trying to extend this sort of no-go result to these theories. And there's a couple of things you can already do. You know Galilean won't solve the problem. Maybe these higher powers in X will, but I think, well, that's something we want to take a closer look at to see really what
it's not necessarily even a power law. You know, if you really check what could be, for example, if you treat quiescence as a fluid, and you ask what is the function p of x, which kind of naturally appears for fluids. If you go away from just normal radiation, so basically p is equal x squared, then any other real fluid which you try to model will have horrible expression, non-analytic, with square roots. And that's for simple, really most simple known equations of state.
What do I gain then over just doing dark energy, ks?
Exactly.
Yeah, so but that's but that's the point, right? I can just, of course, I can just take the G2 term. I can have the potential. I can.
But what I meant, I can also take G3. That's the point.
Yeah, but that's what we want to see is if it really does anything, at least the background level. Is it really a modified gravity theory in the sense that, okay, let's put it this way. Is the self-acceleration, or is the cosmic acceleration in this modification really something that can be attributed to the modification itself, and not from essentially some implicit dark energy that you've added? I want to just say this because...
but it's humanly coupled, right?
Yeah.
So the acceleration is the acceleration of
No, but I mean, if you look at the background, right, it's not that clear, because that's the background. You can always add dark energy and then put in some coupling to your dark energy at a small level, which will never be observationally you will never observe, and you can say, oh, look, this is cosmic acceleration for modified gravity, but it isn't. It's dark energy, and you've chosen to couple it a bit.
Sorry, wait a second. You chose to define this self-acceleration as being acceleration in the Einstein frame.
No, Jordan frame, not Einstein frame. So the point is you can have a coupling, but the coupling must be large enough that it can't do anything, right? It must be an order unity effect.
In these models, there is only the Einstein frame and the Jordan frame are the same. And therefore, if there is an acceleration,
no, exactly. That's what I'm saying. But this is a different definition of cosmic. That's what you're talking about is a kinetic acceleration. Right. But you can, no, you can. No, I mean, I don't think I agree with this because.
What? Well, I mean, let's move on. So let's talk afterwards.
Okay, yeah, sure.
What was I going to ask? Okay. Yeah, this is all at the level of EFT, which of course doesn't have screening. This is probably a long shot, but do you have any idea if screening stands any chance at playing a relevant role in
Well,
this gravitational wave?
yeah, so there's two things, right? The galaxy SW is basically testing the largest scales in the universe.
no, I'm talking about the
That's
gravitational
one,
wave part.
yeah, that's one thing. The other thing is a measurement at 40 megaparsec. Okay, I mean, you could maybe come up with something that can hide this, but it's also, I mean, then you also have these other hints from cosmic rays, right? I mean, how do you want to screen something from having some order unit effect to going to something which is 10 to the minus 15? I think 10 to the minus 17 constraint that I showed is actually a conservative constraint that assumes that these cosmic rays come actually from the galaxy. If they come from outside the galaxy, I think it's even 10 to the minus 23. So it must be very efficient screening effect. I'm not saying it's impossible, but that's also why I actually call the whole thing challenges, not really, it's not ruled out yet.
Well, okay, let's go.
So can you just explain again how you define omega in the EFT? I mean, what's your Einstein frame? How do you define the Einstein frame?
No, I mean, essentially, I didn't show this. This is the EFT expansion that we had, that Filippo talked about, I think Joe talked about, Emilio. You get these first you get the background terms, like the first, zeroth and first order perturbation interaction. And this is the first term that appears there, is the factor that multiplies your Ricci scalar. It's an effective term. But there's different terms from the thing is that if you go look at the full Horndeski theory, there's different terms that give you contributions to omega. So it's not as simple as just saying it's G4 phi. There are other terms that contribute. And you can't always define directly an Einstein frame. That's why I'm saying it really only needs to apply to the background, because cosmic acceleration is something we see in the background.
Okay, so thanks.